Welcome to the second part of our tutorial videos. In the first one, we talked about how to set up the analysis in the tool, and now in the second one, we will discuss interpreting the results. If you did not see the first one, it's available on the EOMOR website. And just as a reminder, we are working with the EOMOR motor model in version 1.3. And just as information on the EOMOR project, EOMOR stands for European Motor Renovation Initiative. It's a project funded by the European Union under the LIFE program, and the aim of the project is to accelerate the replacement of old, inefficient electric motors in industry and the service sector. And with that, we jump back into the tool. We have by now finished our calculation, and we can see the results directly on the dashboard. We see results divided into those on individual motor level, on stock level from 1950 until 2050, and also for individual years on the stock level, so from 2000 until 2050. And also we get a bit of information provided on how information programs would compare to the financial ones which we're calculating here. Let's start with the results on individual motor level. We see here that the subsidized motor which we selected is an IE4 motor in the power class of 0.75 to 7.5 kilowatts. The purchase price of this motor would be 483 euros based on the background data in the model, which means with our 50% funding rate, the company still have to pay 241.50 euro, and it's the same amount that the program is funding to the companies. We then get a bit of information on the years until amortization for the motors, and this is merely meant as orientation for the user of the tool to then jump back and change the input parameters. So it basically tells you, without a subsidy, replacing an IE1 motor with an IE4 motor would generate yearly electricity savings of 128.21 euros, which results in 3.77 years until amortization. And we also get the internal rate of return, and we get the same if we apply the policy. It is meant for you to decide then which motors should be replaced. So should you fund the replacement of IE1, IE2 or IE3 motors based on the savings which can be generated, which are of course changing depending on which power class and which motor types you selected. As a last note here, those values are calculated assuming a 20-year lifetime of the new motor, and also of the old motors having no residual value. That means the savings that the new motors generate are distributed evenly over those 20 years, and we do not get any money back from the old motors which we replace. Just as the background assumptions to have that clear. The more important results are on stock level, and we see them here. They are calculated for the entire modeling time frame. So we have a base case scenario with no policy, and then we compare this to this scenario with the policy intervention and see what the changes are. And we find that for our program, which has a volume of 2 million euros, we are able to replace 8,282 motors, which generates energy savings of 40.8 million kilowatt hours, or in kilotons oil equivalent at 3.51, which then results in a program efficiency of approximately 5 cents per kilowatt hour saved. We also generate environmental impact savings, which here accumulate 15.7 million kilograms CO2 equivalents, more or less. And also the last information provided here is the material demand, because we are replacing with IE4 motors, which have a higher copper demand. Additional materials of 23,000 kilograms of copper is needed. Here we have to note, and this is important, that we do not take into account the recycling of the old motors. So of course, if you recycle the materials, maybe the material demand for those new motors can be partly recovered. For the industry or for the end user, this calculation results in energy cost savings of almost 7 million euros, and also in additional investment costs for the new motors of 1.6 million, which generates total cost savings of approximately 5 million euros. We then have the results on stock level for the individual years. So as I said, from 2000 until 2050, we have the results for energy consumption in kilowatt hours, in kiloton oil equivalent, and also the environmental savings in kilograms CO2 equivalent. So if you're interested in the data per year, you can extract it here. And the last information provided here is how might an information campaign and capacity building compare to achieve the same energy savings. And this is based on the experience from existing programs, which means we are taking the cost efficiencies ratios, which are available in the literature for other programs and apply them to the savings we generated with our financial scheme here. And this all gives us a range of broadly 200,000 to 600,000 to set up an information campaign and capacity building scheme to achieve similar savings. Of course, here it has to be stressed very much that this is just meant as an orientation. And of course, it's not intrinsically calculated inside the model. It's merely to give you an indication of how might an information campaign compare. And we also provide a bit information here on the different programs, so on the 2 financial programs, subsidy scheme and tax incentive, with again a bit of explanatory text also for the information campaigns and capacity building. So much to the numerical results. We also have graphical results. For this we changed the tab. We see here we have them on sales and stocks data, on materials, on environmental impacts, and on economic impacts. The sales and stock data provide you with information on the input motor stock of the model and also the share of different IE classes. Also then based on this, on the calculated sales and the stock per lifetime. So basically it gives you a bit of the background information with which the model works. I will directly move down so that we have the material section. So we have the materials entering the market, the material currently on the market and leaving the market. And this is only for the material which we have selected, which in this case is copper. And we see we have the base case compared to the scenario. As we see here, since we decided to not use any VBA in the calculation, this might require manual editing of the axis, as you see here. And how this is done, you click on the graph, you adjust the axis. So in this case, it should be around 50 million, the maximum probably. So we move the maximum 5, rescale, and we see that now we can see actually the copper for the base case and in the line, then also the scenario. Because we're only changing a small share of the motors on the market, the difference between the scenario and the dashed line and the base case is very minimal. We also have the results on the environmental impacts. So we see here also the comparison of the base case against the scenario. We have on the left graph here, we have the electricity consumption and the global warming potential and CO2 equivalents. The 2 graphs run in parallel because we use emission factors, which means we have the CO2 intensity of the electricity mix, which is the background data information, which also, by the way, can be changed. And I get back to that in a bit. So here's the information on the base case, here's the information on the scenario, and here's the difference between the two and the savings. Here actually we provided you with the maximum and minimum values for the axis of this graph to make it even easier. So in this case, we know that the left y-axis, the minimum should be minus 2.6 million. So we can change it actually and say we have minus 2 here, 0.6. Let's do it at minus 3. And the minimum should be at 0. And the maximum values, the right one, is also 0. And the minimum, minus 2 million. And on the left side, I actually did a mistake. So the minimum should be minus 3 million and the maximum should be 0. And here we see we have the graph properly sized. Lastly, the economic impacts you see here also. We have the base case, the scenario, and then we have the difference between the two. I will not go into the scaling here, but I do want to give you a bit of information as the last part of this video on the background information. What we can do is we can make visible some of the hidden sheets. I do this here. And in this case, we want to take a look at the parameters where a bit of the important background data is listed. So we see here the different countries which are possible to model in the tool. We have the EU27 and then the member states. Here we see the country scaling. It works with EU data and we scale it down on member state level based on a scaling factor, which you can see here. And if you have better data available, of course, you are able to overwrite it. You have an option here with manual override, which you can then select on the dashboards. You can put your own values. This way, you will improve the accuracy of your results. Also, you can adjust the electricity price. So here we took values from Eurostat for that, but if you have better data, you are able to change it. And the same is true for the electricity emissions, which we took from literature values. And if you have different values for your member state or for your region, then of course you can exchange them here. And you also find a bit of more information here, which is background information. I will not go into the details here. And with that, I come to the end on this second part of our tutorial series. I hope it helped you to understand the tool. As I said, if there are any feedback, we are very happy to receive it and wish you good luck in exploring the tool.